All right.
It's probably me.
I'm not gonna look for the slowest laptop, but let's actually just roughly look at the, okay, I'm gonna remove the names, everybody. The point of this is not looking at the names. How about that?
That's boring.
That's boring? Okay, just whatever you have to comment about somebody's laptop, just zip it, okay? Here we go. So here are the results. So roughly, so I'm going to highlight me just to put myself on the spot. So basically, Gauss elimination will give you 4,000 around 4.5 seconds. It's somewhere on the order of that, right? And it also depends on what is your laptop currently working on, and is this the only thing that laptop is working on? Then as you go to 2,000, it's going to be 25 seconds, then 5,290 seconds, and 1,600 for the current version of whatever we programmed in Gaussian elimination. And again, you can see that there is a range around those numbers. That range depends both on the hardware and what is that hardware working on in parallel. And then after that, if we look at the NumPys, mine got in 0.09, so not even a 0.1 second, right? And then 0.2, 3, around 3 seconds, and 24 seconds for the light. Now, this is not necessarily Gaussian elimination, probably actually not at all. Okay? We're going to go to faster methods in our next process, but this is just to, we're not going to go into details of speeding things up. This base course is for understanding, but I also want you to understand that not all algorithms are created equal. And even though for most of the things that we're looking at in class, they're fast enough, once you actually get to the solutions of importance, then they're not. Imagine you're flying an aircraft, and that aircraft has to, on the fly, solve a problem that is million by million. Well, your Gaussian elimination will not cut it, right? So we have to wait 1,600 seconds or so for that solution. We'll be halfway over to Dallas by that moment, so it's maybe a little late, okay?
What's the relationship between the change in size of our inputs versus the change in time? So I can't really figure out.
So that's a great question. So this is where this O of n cubed versus O of n squared makes a difference, okay? So when I say I give you a larger problem, 10 times larger, if your algorithm is O of n cubed, the solution will technically be 10 to the 3 times longer. Okay? Does that make sense? Did that sink in? So if I have an algorithm that overall works, its timing works as O of n squared, because that's how many operations I have to solve. Okay? Then when I increase my system size from 10 by 10 to 100 by 100, which is 10 times, my solution will be 100 times slower. Okay? And that's why it's n cubed is so bad, because I increase 10 times, but my time goes 1,000 times. Okay? So that's the importance of algorithms. So algorithms, linear algorithms are the best, right? So when I basically have a problem that increases 10 times, and then my speed roughly increases that many times as well, or maybe linear coefficient times that. That's great. That's not the reality most of the time. Most of the algorithms, the ones that we kind of spit out without thinking, are n squared and cube. N log n is something that we can improve n squared algorithms too. Okay? So that's kind of most of the time the good timing is up to the n log n, logarithm of n. Okay? Now, beyond that, everything is slow, and there are some problems that are so-called NP complete, but they're basically extremely hard to solve in polynomial time. So the problem just grows. Okay? So we have to be careful which algorithms we're solving. Now, I commented when I introduced on LU, so I split this morning, but I also started outputting a video, so that's been going very slowly. So I split up and timed forward elimination step versus backward substitution. When I introduced linear, the LU decomposition, I said that there is a gain in speed up by doing forward elimination step only once, and then just repeating forward or backward substitution for the rest of the problem. And here is an example. Let's just look at 2000. My 10,000, we're still working on it. I started it an hour before the class, but I also started outputting a movie, and that's that has slowed down the entire system. So anyway, there's forward elimination for 2000. The forward elimination part took almost 28 seconds, and backward substitution 1.3. Okay? So this is why it's saving. If I'm going to solve this system 3 times, instead of doing 3 times 30, let's say 90 seconds, I'll do this 30 seconds once and 6 of these because you need forward and backward substitution. Okay? But it's still way faster than 90 seconds. Yes? Do you see the difference? That's because forward elimination step is really when it's O(n) cube, it's slow. Okay? So then even if I'm just doing it 3 times, and I'm not doing it 3 times, on the system of n, right, there's an importance of saving, right? So if I'm repeating even 3 times, but most of the time I'm going to repeat it 1,000 times, okay, on the system of size 2,000. All right, so this is the importance of LU decomposition. Now, quick question for everybody. So this is just to show the things on a graph. So this is graphical comparison of what the solution was on my computer. So my computer is not the fastest of them all. It's a 1.6 gigahertz. So that essentially means 1.6 billion operations per second that it can do at the same time. And I think it has 2 cores, so technically one should be available for Python and the other one should crank that movie, but they are nevertheless have some of the shared memory and they're slow. Okay? So when I do anything else, then that slows my computation down. So you can see how better optimized the NumPy solution is compared to whatever we did, especially as you grow in size. Now, for LU decomposition, we said our basic strategy is the following. If I have a system that I'm going to solve with different right-hand sides B multiple times, then there's time savings in splitting this, doing forward elimination only once, since in the process splitting your matrix into L and U, that is lower triangular matrix with ones on diagonal and upper triangular matrix. We are doing an algorithm with ones on diagonal. It doesn't have to have ones on diagonal. There's no unique way to do this. And then we solve the actual system in 2 remaining steps. One is forward substitution using lower diagonal matrix. So we're looking for D such that LD is equal to B. And B is this right-hand side that I'm intending to change later. And then once I have that D, then I'm solving upper triangular system, which is back substitution as UX is equal to D. Okay? And that's what gives me X. And I can repeat that. Now, in your homework that is due today, you had to, is it due today or on Monday? Oh, okay. Okay, good. No problem. No problem. I thought somehow that it was 2 today and that I didn't introduce matrix inverse. All is well. So you will also have, didn't I give you a shock now? Relax. So there is matrix inverse, okay? So this is one example problem where I will definitely have to use this strategy. So why? Technically, if I'm looking for the inverse of the matrix, and by definition, it's another matrix such that however I multiply that inverse of the matrix times my matrix A or A inverse, I'm going to get an identity matrix. Okay? Everybody sees a typo on my slide in the first line? This is the first time I see it, and I've been using these slides a lot.
I instead of
I and 1.
Yeah.
Mathematically, it's correct. Identity matrix is what's called a 1 in the world of matrices, because you multiply the identity matrix with any other matrix, you're going to get the same matrix, which is what number 1 does. So mathematically, this is correct, but it's actually a typo. Now imagine if I've had this code for a while, and I only now, after 6 years of teaching this course, I noticed this typo. And it was 1 instead of an I. 1 is a perfectly valid thing in the code, right? I could write it in any time. So anyway, just an aside. So there's a lot of typos in our codes that we're using. And sometimes they show up where you can see that they're doing things wrong. And sometimes they're just sitting there until they're a problem. For instance, right now. Okay? So this is just a note of bugs in existing software. So anyway, so we're looking for this matrix. And if I have this matrix, then I can actually solve my system directly because I have inverse of this matrix. And there are other cases where it's actually useful to have this matrix. However, often we actually are not busy looking for it because what it really does is when I look at the A inverse is equal to 1, I can actually formulate that. Okay? So when I'm multiplying a matrix with another matrix, it's actually equivalent as taking this matrix A and taking columns, okay, of this other matrix and multiplying it. And then my result is this A times each column. And I put them together as a column. That means that basically my A times, if I had a 3 by 3 system, and let's say that this is my matrix A, then this is, imagine this is the first column. A times this first column, which is first column of inverse, A inverse, has to be 1, 0, 0. Okay. A times my second column has to be 0, 1, 0, because that's the column of identity matrix. And A times the third column of A inverse has to be 0, 0, 1, because that's the third column of an identity matrix. So I'm simultaneously looking for 3 vectors, which are columns of my inverse, such that A times the first one is 1, 0, 0, A times the second column is 0, 1, 0, and A times the third column is 0, 0, 1. Does that make sense? This is essentially an expression of multiplying A times A inverse, and this being columns of that inverse, right? So this is my first column of A inverse, this is my second column of A inverse, and this is my third column of A inverse. And doing this multiplication is essentially multiplying A times each columns, and then making it equal to the columns of my identity matrix, which are 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay? So I need to simultaneously, in this case, solve 3 systems that have the same A, but they have a different right-hand side, correct? And this is perfect for LU decomposition. Okay? Let's get at it. Take a piece of paper.
So the answers I'm getting, the first one will be my first column.
Yes, yes. So you're solving 3 systems. And your first system, and basically Ningyu and I will walk around and look over your shoulder. But your strategy is the following. You will first decompose this matrix A into this L and U, and you will use a very specific forward elimination procedure that we worked on last time. So having papers from last time would be helpful. And then after you have that, L and U, so again, this is my L and this is my U. After you have that, then you solve these two systems by hand, just forward and backward substitution. And you will get your answer x1, x2, x3. So you do this only once, and these two steps you do for every right-hand side. This one, and that one. Yes? Okay, so let's do first this LU decomposition. And if you need help or have any questions, just please raise your hand and they will show up. Oh, okay. Yes.
I don't know my answers correct, but
Sorry, so you need actually this V needs to be 1 0 0, then 0 0 0 1 0, then 0 0 1, not this. This slide. So let's see.
I made L.
This is I did.
You use this normal. You just like use like upper diagonal, upper triangle diagonal. And L is the lower, but you use 1 1 1 instead of 1. No, just for the lower. Well, I think it's just for the lower. You multiply this too, it would be 1 0 0.
Yeah, I know that.
Look, there's row times column. Yeah, this row is column plus row to column plus row to column. So technically, these two add up. They add up all together for. It's the whatever. You get L and U. Next year. Oh no, I took that last year. I mean last year. I mean, you're here with
Like that next week.
So did everybody get L and U successfully in whatever is actually shown there? Yes? This is your checkup. This is not just given to you. If you don't know it, you have to come up with it. So once you do, repeat these two steps 3 times with 1 0 0, 0 1 0, and 0 0 1. You can solve this too. No harm done. Just a little extra work. Yes?
How do you get L and U again? You use these words?
Yes. Oh, so you just
I thought you
it's just an exercise, not a problem. So you just solve this process part, which is okay for this solution. But I want you to get L and U.
Oh, okay. Yeah, I get it. I thought you split it up.
No. So do not just split.
So it's more than
You wish it was that simple. Okay? L and U taking the lower the triangular part of A and upper triangular part of A. You have to go through forward elimination to get it. It's like, oh no. Yeah, let me just do. So I want to give this.
So you multiply this row minus 7, and then so 3 multiplied by minus 7, minus 21.
So I do forward elimination. So I use this one.
Minus 21 plus 9.
So I replace this one.
Minus 21 plus 9.
2,
Minus 4 over 1. Minus 4 plus 9.
you go wrong with this one. And I, all of this is not really strict what is my choice. Because I'm following an algorithm to actually assemble.
Numbers make
So
sense.
those are the things that
So I did it wrong, so I got it right.
So this is your L3 one. You kind of just record it. L. And it's gonna have ones in there.
That's how we do
That's
it.
what it's gonna do. So this is gonna be 4. So this one is not performed. And then you will here.
But we need to get it.
And then some other here. And then we'll replace the slot with
And we didn't get it. Oh, if you multiply by 7.
and then which is another the other one is too brittle. Then you will have actually this but this new this and you go.
Okay, yes, I'm almost
All that.
Just algorithm time is so smaller than like, what if you just make A into just this,
But that's not correct. You can, but you're not gonna, you need to have multiplication L times U, otherwise it doesn't work. What you're doing is L plus U,
I got an.
Oh,
okay? But that's not gonna solve the system.
oh, I thought we just just get A to be that, and then just solve for X.
And I show you what we do, I do, when you're doing solving algebra, right, that's work. You're solving X, so this is 0. And that's L U X is equal to B. So that's what I'm putting. So you're looking for D, such that L B is B, and then so when this is multiplication, it works. If it was L plus U X is equal to 3, and I'm not quite splitting here, I don't know how to do that. And I don't have a unique way to do that. There's just an algorithm here. Does that make sense?
Yeah.
So this, unfortunately, it's always a little harder. You would like it to be, right? But that's why it doesn't work.
Yeah.
You have to divide by your pivot element 1.
But that's how you're.
So 1 is your A1. That's the element. That's the pivot element. It can be, but here we're trying to be structured so that we don't make a mistake.
We're starting from scratch.
Sure, this gives us that L part. And I didn't prove it to you that that really is the case, but you can actually multiply at least the first row to get the first element.
A1, 2 over H.
So again, we don't want to go through the proof, but this actually then really gives you.
We came up with this, right?
Times U. And it has to work for matrix multiplication. Not element-wise, but the proper matrix. First row times first column, first row times the second column, first row. The whole.
Anyway, there's, I'm still having problems with my.
No, you know, U. Your U is whatever is, so when you get this is what you got. Are you sure? 4 minus 4 times 1 is 0. 5 minus 4 times 2 is
4 times 2.
2.
I just subtracted 4 out of
I see your brain on a Friday just wants to do all these shortcuts that are cute but don't work. And I agree, my brain on Friday is similar, but you know, that's not what works.
Yeah. Now I got negative 3.
Okay. Wait, how'd you get that?
So have you gotten through LU?
No.
Oh, wait.
Check,
Why is it
multiply, put this in, put A in. Oh, you can multiply by case, but that's in Python. Check with Python whether you got the correct thing.
So we were using the wrong
Yes, because when you actually multiply things, you can kind of prove it. It's very easy to see the very first element. So we were after that, we get to the now multiply by u has to be the correct element.
Oh, really?
And if you actually put it, yeah, and if you put these coefficients and multiply things with each other, you can solve it. Well, it should be worse than like thirds.
But I think it's
And this is about that.
2 equals
Had like thirds of that. So yes, check your accuracy. And you can find what solutions are by this Python. So check yourself
Yeah.
in Python if you'd like.
I checked 4. Okay.
Has everybody gotten LU decomposition? No? Who still has trouble?
Well, I think
There we go. So now we do this, but you gotta
divided by
kind of record what you're doing. With this one, you would raise this row to 5 2 minus 4 over 1. This so you kind of have to record them, which is whether 3 over 1.
No.
So now if I was to send out L, I would
I divided.
now I have
Yes, it's up.
Yeah, they 3 2.
Like that, so.
Actually, I think that was the hardest thing. That was the hardest thing. But in general, you move to system of linear equations.
and then you have L and everybody has gotten L and U?
Argentines, you took that out.
Oh, I think I got it.
Well, no, but there's later on, like, conceptual.
Oh, no,
I had an A, that was fine, fully down.
Yeah.
It's just, do you like it?
He looks like pretty often.
I don't know what it is.
It's so funny,
Because
man.
L multiplies L
It's funny.
What is that? Oh yeah,
Like A1, 2.
It's like French fries.
He's from Belarus. What's that? How's that, German? No.
But yeah, I think that's the best way to describe it. Like something.
It's calling my road.
But I heard better.
And now you need this lot. This is something.
Accessory game, seeking one, I don't know. It's just retail.
So you eliminate, it's the best.
I remember first day you did the show was surfing. He was like, look at this. He was like, no, not surfing. It was like showing the results of like other years. Like, everyone gives me better than me. But sports, I can show you this. Oh, that's the start.
So this is your previous element.
So
Wait, you don't get to
Yes.
no,
So I started with this part.
yeah, that's it. Pull up all 2018.
Oh, yes, you're right. So that's
my
only one.
one.
You're right.
Now,
I don't know what this is.
So then start with then in the farm.
This vector, then this vector, so this is my N, we'll do it, now it's my U, this is my L vector, so is this the right response? This is my L. And then we'll just do going up with the
Yeah, so you need to get something like this.
oh, you know what? You're right.
Yeah.
Yes.
And let's check. So again, my L, if my notebook, well, my notebook is not. So my L should be this, and my U should be this. So U is the result at the end of the forward elimination. That's what's left of my matrix A that I transformed. And this one, you put ones on diagonal, and you record coefficients you used. And please follow the structured algorithm. So this is your essentially A21 divided by A11, this element. So 4 over 1 initially, 4 over 1. And this is your A31 divided by A11, so recorded in there. This is not the original A32 over A22. It's not 2 over 5, but it is after I transformed my matrix, I have these new elements in this place, and this is what you should get 4 over 3 as that coefficient. So this is your L, and you can, I was about to type this into, but my thing is not necessarily very responsive, so import numpy as np. So if I define L as np array 1 0 0 0 4 1 0 and 4 over 3 4 over 3 1. So that is my L, and my U is NP array. Uh, 1, 2, 3, 0, minus 3, 1, 2, 3, 0, minus 3, minus 6. One. Then when I multiply the 2, I should get my matrix A. Is that correct?
Yes.
So don't split A into L plus U. That just doesn't work with what we're doing. Okay? Now you're actually going to solve this with the right-hand side 1, 0, 0. So basically these 3 problems. Okay? And this should be easy. So 1 times D1 is 3, D1 is 3, and so forth. So once I get these, actually 1, 0, 0, so D1 is 1. So once I get these, so basically if my E1 is 1, 0, 0, NP array, then my D, the first one, is I'm going to just go with LinAlg solve of my L and E1. And I should print it. So you should get 1 minus 4 and what is this? 10 over 3? No, 7 over 3. For the first D. And then your X is this is your first X. 2 over 3 minus 10 over 3 and 7 over 3. Okay, so for your quick checkups, this is, I'm walking through slides. For your quick checkups on solutions to linear systems, if you don't want to rely on your Gaussian elimination and want something a little more robust, you can always use np.linalg.solve, np.linalg.in. So this will actually give you inverse of the matrix, which if it exists, it is unique. Okay. So just proceed this and finish. So I rely on you to be able to finish it up. Now, for projects, I will, after the class, send you a sign up from Sign Up Genius. It's called an online thing, where you will find pair up. And there will be only one group that will be allowed to have 3 people. Otherwise, pair up for computational projects. We're going to release what the computational project is next week, but I want you to Monday to find a pair for your computational project. So whoever you think you're going to be a good teammate with. Okay? So I will and split up the work. Okay? So I do expect you to work together and figure out who's going to work on what, and you will actually have to write down what was done by each. So please sign up, and then on Monday I expect you to be signed up. So if you didn't get an email from sign up, let me know, because that may